Have you ever actually wondered what happens under the hood when you hit run on a piece of code? I mean, really happens. Well, welcome to this explainer. Today, we're taking a thrilling, top-to-bottom descent into the journey of a computer program. We're going to track exactly how a simple human idea transforms into raw physical electrical impulses. It's a pretty wild ride, so let's just jump right in.
Just to give you a quick roadmap, here's our agenda. First, we'll look inside the computer's brain. Then we'll introduce the C language, compare compilers versus interpreters, break down the 4 compilation phases, and finally, look at executing code in memory.
Okay, part 1, inside the computer's brain. We really need to understand the hardware foundation before we do anything else.
So before we can even think about translating our ideas, we absolutely have to understand the physical canvas we're working on. Now, most personal computers are built on what's called the von Neumann architecture. In plain terms, it's a stored program design where both your instructions, what you actually want the computer to do, and your data, the information it's working on, are stored in the exact same memory space. And because they live together in that same place, they have to share a single digital highway or system bus to travel to the processor.
Think about this layout. The central processing unit, the CPU, connects directly to a central memory unit. To get any actual work done, the CPU has to run on a loop. It repeatedly fetches an instruction, decodes it, and then executes it. But here's the catch. Because of that shared digital highway we just talked about, the CPU can only do one thing at a single time. It can read an instruction or it can read data. It can't do both. This literally creates a traffic jam, which is famously known as the von Neumann bottleneck. And yeah, that definitely limits your overall speed.
Now contrast that von Neumann bottleneck with the Harvard architecture, and you'll see a massive difference. While von Neumann uses that unified memory space, the Harvard architecture physically separates things. It has one memory unit strictly for instructions and an entirely independent one just for data. Because they have independent buses, the CPU can fetch an instruction and read the data at the exact same time. Obviously, that vastly improves your processing speed.
So you might be wondering, which one do we actually use today? Well, modern hardware kind of gives us the best of both worlds. General-purpose processors, like the ones from Intel, AMD, or ARM, don't strictly follow just one pure architecture. Down at the core level, inside the L1 cache, they act like Harvard. They split the instruction and data caches to maximize that blazing fast processing pipeline. But when you zoom out to your main memory, your RAM, those caches merge back into a unified von Neumann layout. It's a hybrid reality, and it keeps our system design incredibly flexible and cost-effective while still seriously prioritizing speed. Moving on to part 2. Enter the C language. Let's see how we bridge this gap. Since our hardware really only understands raw electricity, we need a reliable way to actually communicate our human logic down to it. And this brings us to an absolute titan of computer science, the C language. Created by Dennis Ritchie way back in 1972 at Bell Labs, originally to implement the Unix operating system, by the way, its procedural, step-by-step approach heavily influenced modern heavyweights. We're talking Java, C++, Python. Even after 50 years, it remains the absolute foundation of modern software.
C is fascinating because it acts as a unique mid-level language. It essentially bridges the massive gap between highly readable, high-level human concepts and low-level hardware manipulation. On one hand, you can write clean, logical functions. But on the other, you have the raw power to directly manipulate physical memory addresses using tools like pointers. It's a real game changer.
All right, part 3, compilers versus interpreters. It's time to translate that code. Now, obviously, the computer can't just read your typed C code directly. It needs a translator. And we generally have 2 main ways to pull this off: compilers and interpreters. C uses a compiler. This means it translates your entire source code into an independent, blazing fast, executable file all at once, long before you ever run it. Contrast this with an interpreter, which languages like Python use. An interpreter translates and executes code line by line right on the fly. If it hits an error, it stops immediately, and it doesn't produce a separate binary file. C's compiled nature is exactly why it's so incredibly fast and efficient for hardware.
Let's dive into part 4, the 4 compilation phases, getting from code to an executable file. So let's speed things up and watch our hero, a single line of C code, survive the intense 4-step pipeline required to become a real executable program. Phase 1 is pre-processing. This expands macros and strips out all your human comments. Phase 2 is compilation proper, where the code translates into an assembly file. Phase 3 is assembly, converting that into binary object code. And finally, Phase 4 is linking, which spits out our fully baked executable file.
I want to focus on step 2 for a second because it is particularly rigorous. The compiler doesn't just blindly translate your text. First, lexical analysis converts your code into tokens. Then, syntax and semantic analysis step in to check your grammar and verify your variable types. But the real magic? That happens during code optimization. The compiler actively improves your code. It strips out dead code, folds constants, and optimizes your loops so they run vastly faster. Only after this intense cleanup process does it generate the intermediate assembly language.
Fast forward to the final phase, which is linking. Once the assembler creates an object file containing your machine code, it still isn't fully ready to run. Why? Because it doesn't know where external functions, like your basic print commands, actually live. So the linker snaps everything together like giant puzzle pieces. It combines your specific object files with pre-compiled system library code, resolving all those memory addresses. After that, the code is completely ready to run as a single, cohesive package.
To really grasp the scale of this magical transformation across those phases, think about how our code starts out. You type something in a high-level language, like total equals x plus y. This is highly readable, it's a human-friendly mathematical idea completely independent of whatever physical hardware you happen to be using at the time.
But then, through compilation, it drops down a layer into assembly language. Now it looks something like MOV AX bracket X and ADD AX bracket Y. At this stage, it's no longer hardware independent. This is architecture-specific code, explicitly designed for systems programmers to act as a bridge straight to the hardware.
And here is the final impact, post-assembly. Our original human logic, entirely stripped away. It's been transformed into raw machine code, just pure binary ones and zeros. These digits represent the exact raw electrical impulses that the CPU circuitry is going to physically process. It's pretty amazing when you think about it.
Finally, part 5, executing code in memory. Let's actually run this program.
Now the operating system is ready to take our newly forged binary executable file and load it right into physical RAM. During this handoff, the OS acts like a meticulous organizer. It divides the RAM into discrete, highly functional regions so our program can live safely. You've got the text segment, which strictly stores your read-only compiled machine code. The data segment houses your global variables. The stack dynamically handles local variables, automatically growing and shrinking as needed. And the heap? That's a specially managed segment reserved for dynamic memory allocations that get requested while the program is actively running.
Okay, so once the RAM is perfectly organized, the processor needs to know exactly where to begin. It zeroes right in on the initialization offset of the main function in your C code. The CPU's program counter registers this specific memory address because, well, the main function is the undeniable mandatory starting line for execution. The computer basically takes a digital breath, and the race begins. Bringing our whole journey full circle, the processor now utilizes that exact same fetch, decode, execute cycle we talked about at the very beginning with the von Neumann architecture. It fetches the machine code from that main function address, decodes those ones and zeros into circuitry logic, and executes the operations. And it's going to repeat this cycle millions of times a second just to bring our code to life.
Having journeyed from abstract human logic all the way down to the raw electrical impulses of a compiled C program, it really makes you pause. C has been our trusty bridge for over 50 years, perfectly matched to the von Neumann and hybrid architectures we use today. But as hardware rapidly evolves, pushing into wild new territories like parallel computing and neural processing units that totally defy standard architectures, what exactly will be the next universal language? How will we translate our thoughts to the machines of tomorrow? Think about that for a bit. Thank you so much for joining me on this explainer. Keep focusing and keep learning.